Hi, this is Mr. Zachary, and we are looking at question number 23. This is the one with the bouncing ball and the coefficient of restitution. This relates how much energy you get back out. So this is a ball bouncing. Its highest point is point A up here. B is just before it hits the ground. C is just after it leaves the ground. And D is at its highest point again for this next bounce. Um, Ignore the horizontal movement. That just makes it so that we don't have overlapping stuff. As we look at this, some things, we know that energy is conserved until it hits the floor, like from A to B, but we're not so sure between B and C. And because it only goes up a part of the way, we are pretty sure that energy is not conserved between B and C. If it was, then the ball would bounce just up to the same height as it did at A and continue to do that along the way. So it's not conserved between B and C, but it is between A and B and between C and D. So if I look at this, it tells me that the height at A is 7 meters, or 0.7 meters. I know the velocity at A is 0, because again, we're ignoring horizontal movement. And there's no spring. At B, the height is 0. It's just about to hit the ground. I know it's moving, I don't know the velocity, and again, there's no spring. So I can say the total energy between A and B are the same. The total at A is the total at B. And so gravitational, it could have gravitational, it could have kinetic at each of these points. I know there is no kinetic at A. I know there is no gravitational at B. And so I can cross those out, and I get that, plugging in the numbers, I get the velocity at B is about 3.74 meters per second. That's for part A. For B, rebounds up to point D, how fast must be going? Well, I know that the height at C is 0. It's just coming off the ground. I don't know the velocity at C. That's what I'm looking for. I know the height at D is 0.4, and the velocity at D is 0 because it's at that highest point. What I can say is, because of that, I can say the total at C is the total at D, and that types of energy it could have at each of those could have gravitational, could have kinetic, could have gravitational, could have kinetic. But because of this, I know that there is no gravitational at C, and I know there is no kinetic at D. And so I can just cross those out. Those are 0. Setting the kinetic at C equal to the gravitational at D, notice that the mass, each of these has a component that is the mass. But putting in the numbers, I find that the velocity should be about 2.82 meters per second. So it hit going 3.74, and it left going 2.88, which means it lost some energy. How much did it lose? Well, now what I can say is that the total at B is equal to the total at C plus whatever it lost, that energy that must have turned to heat or something else, because the collision lost some energy out of the can cone. So I can say that the total energy at B, which looking back up here, again is just kinetic, is equal to the total energy at C, which here is just kinetic, plus whatever was lost, whatever energy was lost. Using the values I found from A and B, I can put in the numbers, find out that there were about 0.6 joules of energy that were lost in the ball hitting the floor. Now, how efficient is that? Well, I know that efficiency is how much energy out divided by how much energy we put in. So we put in 1.4 joules. We got out 0.8 joules. And so the efficiency would have been about 57%.